measured and also what we have already measured at optical, in the optical band. Okay, so intrinsic polarization. Well, we expect that the radiation emitted by the star surface layer, by the neutron star surface layers, is polarized because neutron stars do have a strong magnetic field. And the strong magnetic field acts in changing the photon particles cross-section, and so the way in which radiation interacts with matter. And second, because the presence of a strong magnetic field alters the electric and inverse magnetic permeability tensors, and thence affects the way in which radiation propagate in a cold plasma plus vacuum medium. And this is shown here by the structure of the wave equation. And of course, this is the inverse magnetic magnetic permeability tensor. This is the electric tensor. In general, radiation coming from a neutron star transverses a cold plasma plus vacuum medium, and which is magnetized. And in general, radiation is expected to be elliptically polarized. However, if the photon energy is much smaller than the electron cyclotron energy, the two normal modes of polarization are almost linearly polarized, and they are called the extraordinary or X and ordinary or O modes. This is a cartoon which shows how the electric field of the radiation oscillates, the direction in which the electric field of the radiation oscillates with respect to the plane made by the local direction of the magnetic field and the propagation vector k. The extraordinary photon has the electric field which oscillates perpendicular to the plane made by Z or K and B, while the ordinary photon oscillates in the plane made by the propagation vector and by the local value of the magnetic field. The opacity properties of the two modes are dramatically different in the sense the O mode opacity is almost unaffected by the presence of the magnetic field, which means that the O mode, the ordinary photons, interact with matter as normal unpolarized light in absence of any magnetic field, while the X mode opacity is strongly reduced with respect to the unmagnetized case by a factor which, roughly speaking, for scattering, this is exactly the dependence goes like the photon frequency square divided by the electron cyclotron frequency square. So if omega is much less than omega c, the opacity is strongly suppressed. Of course, if talking about surface emission from neutron stars or surface emission from a neutron star which crosses a magnetosphere in which there are charges, the intrinsic polarization depends on the surface emission model that we think applies for our neutron stars, and of course also on the possible role of matter, of electrons which circulate in the magnetosphere. There are actually two basic models which we can think describe correctly, although we don't know which is the really correct one, the emission coming from the surface of a neutron star. Either we think that the neutron star surface is covered by a gaseous atmosphere, or the neutron star has a sort of condensed surface in the solid or maybe liquid phase. In this case, it is called a bare neutron star, and this bare neutron star is maybe covered by a thin hydrogen layer. There is a very nice review paper by Sasha Potekin on this. And the emission properties, of course, and the polarization properties strongly depend on the choice of the model, of course, and also on the local value of the magnetic field and on the temperature. If you know, because you selected the model also for the distribution of B and T on the surface besides the emission model, then you can calculate the polarization degree at the emission, the intrinsic polarization degree, simply by computing the difference between the flux in the X mode and the flux in the O mode and normalizing this to the total flux. Then if you would like to have an idea of how much the light coming from the surface of our neutron star is polarized, you can divide the surface into patches and sum up and up those which are in view at a certain phase. And of course, this will depend on the orientation of the neutron star and also on the angle which the neutron star makes, the neutron star spin axis makes with the dipole axis. So everything will depend on these two angles, which I call psi and chi. This is the neutron star spin axis, this is the magnetic axis, this is the line of sight. And of course the neutron star, come on, okay, is spinning and is showing different areas during the spin movement at the different phases. So here are two examples of what comes out from this kind of calculation. This is the intrinsic polarization as a function of the two geometrical angles Xi and Chi for the condensed surface. This is the same from a completely magnetized, magnetized, fully ionized hydrogen atmosphere. And you see, of course, that the intrinsic polarization is completely different in the two cases. I mean, the shape could be somehow similar in the two cases, but if you look at the absolute scale of the polarization degree, that's fairly different, as you can see. Okay? In this case, the intrinsic polarization is much higher than in the other case. Okay, what is the observed polarization signal we can expect once we know how to describe the intrinsic polarization? Well, let me just remind, this is a rather obvious point, that the polarization is most conveniently described, or better polarized radiation, is most conveniently described using the Stokes parameter. These are additive quantities, and of course the Stokes parameters, which are listed here, the intensity, total intensity, Q, U, and V, are expressed through the complex components of the electric field. And let me just point out that the normalized Stokes vector, so the vector made by Q, U, and V, for linearly polarized radiation in the X and O mode is just written in very simple terms as 1, 0, 0 and minus 1, 0, 0 for the extraordinary and the ordinary mode respectively. I'm going quickly through this. The fundamental point one should recognize and bear in mind is that each photon is polarized in the ordinary or extraordinary mode, but it is so polarized with respect to a frame XYZ, which is defined by the propagation vector k and the local direction of B. Of course, as the photon propagates, the local frame XYZ changes if B varies. Of course, k remains always the same, because this is, of course, the line of sight direction. But if B changes, the local frame changes. So before one can add the Stokes parameter of the single photons to compute the polarization properties of the entire radiation, there is a very important operation that needs to be performed. One must rotate the Stokes parameter to bring them in the same reference frame, which is the polarimeter frame, which is defined by three axes, U, V, and W, where, of course, W is in the direction of the line of sight. Here is a cartoon which shows you through this drawing what I said before. Here are 2 points close to the neutron star surface. The direction of B is different in the two cases. K is, of course, the same. These two Ks are two parallel vectors. And if I build up the two reference frame, X prime, Y prime, and Z, X prime prime, Y prime prime, and Z, the two reference frame are different because, of course, the magnetic field is not the same. So what I need to do is to rotate the Stokes parameter by an angle alpha prime if I want to refer to the first point, or alpha prime prime if I want to refer to the second point. The rotation of the Stokes parameter intrinsically tends to produce a depolarization of radiation. So if you start with a source which emits, with a neutron star which emits from its surface 100% polarized radiation, just because the surface of the neutron star is not point-like and the magnetic field is changing direction along the surface, the radiation you observe will not be 100% polarized, because you need to rotate the Stokes parameters. Okay. So these are just the very simple formulas which relate the Stokes parameters in different frames, which describe the rotation of the Stokes parameters. In our case, they simplify to this form, because for X and O photons, only Q is different from 0, which is either +1 or -1. So, I mean, starting from this expression, one can derive very easily which is the total Q and the total U for radiation emitted in different points along the star surface. Okay. And of course, it depends on alpha, and alpha will change according to the different positions on the neutron star surface or close to the neutron star surface. So, I mean, putting everything together, one can conclude that the polarization properties of neutron star emission are described by two parameters, by two observable quantities, the polarization fraction and the polarization angles that are quite simply related to the Stokes parameter Q and U. Pi L is simply the square root of Q square plus U square divided by the total intensity. If I use the normalized Stokes parameter, it's simply the square root of the sum of the squares of the normalized Stokes parameters. And of course, the polarization angle is 1/2 the arctangent of the ratio U over Q. And let me point out that there is just one case in which the observed polarization degree or polarization fraction and polarization angle coincide with the intrinsic ones. And this is the case in which the angle alpha I, which the magnetic field, which we need to rotate the Stokes parameter, is the same for all the points, as, for example, in the case in which the magnetic field is uniform. If not, as we expect around the neutron star or on the surface of the neutron star, the rotation must be accounted for. Of course, the rotation of the Stokes parameter is not the only effect which contributes to make the observed polarization signal different from the intrinsic one. The second very important one is that the magnetized vacuum which fills the space around a neutron star. I'm not considering in this case any contribution from matter, so it is a polarized vacuum. According to QED, this vacuum is polarized, so it's full of virtually plus and minus pairs because of the presence of a very strong magnetic field. The first consequence is that this modifies the dielectric and magnetic permeability tensor of the vacuum, which in this case behaves like a birefringent medium. And this can be actually seen by linearizing the wave equation, that is to say, using the geometric optics approximation. And if you do that, you obtain a set of ordinary differential equations which govern the evolution along the ray of the complex amplitude of the electric field of the wave. These are the vector A, which has component AX, AY, and AZ. And of course, this differential equation which governs the complex amplitude A of the magnetic field can be translated into a set of differential equations which govern the evolution along the ray of the Stokes parameters for photon which propagates along the ray in vacuo. And these are the three equations which describe the evolution of Q, U, and V, the three Stokes parameters. A few words about the different quantities which enter in these equations. K0 is just omega over c, the photon frequency, so this is the photon wave number. This quantity delta is proportional to b squared, and of course z is a coordinate along the ray. In order to see qualitatively how the Stokes parameters change along the ray, one should note that the evolution of the Stokes parameters is governed by two length scales. The first one, let me call LA, is simply 2 over K0 delta, and this is proportional to B minus 2 and the energy of the photon to the minus 1, and this is the characteristic length scale over which the Stokes parameter change. There is a second very important length scale which I call LB, which is simply B divided by the modulus of K times the divergence of B, the gradient of the modulus of B. And for a neutron stars with a dipole field, this is simply roughly the radial distance. And LB measures the length scale along which the magnetic field varies as the photon propagates away from the neutron stars. These two length scales, LA and LB, if you make them equal, they define a characteristic length at which the two are equal, and this radius, which is of the order of few times the neutron star radius, of course depends on the value of the magnetic field and the pole, it depends on the energy of the photon, is called the polarization limiting radius or adiabatic radius. And the condition LA equal LB, as I think is quite understandable, is a sort of divide for the way in which the Stokes parameters evolve in the magnetized vacuum. And this, I think, can be better seen from this cartoon. If LA is much smaller than LB, then we are in the so-called adiabatic region, and the photon polarization mode will follow immediately the direction of the local magnetic field. So a photon which was born as an extraordinary photon, say, will stay in the extraordinary photon mode because it evolves very quickly and it can adapt its polarization mode to the change of B, okay? Of course, as we move outside, then LA decreases, sorry, LB decreases and LA increases, and we enter the so-called intermediate region. And the intermediate region, it is still true that the photon electric field tends to follow the direction of B, but with some delay, so to speak. And finally, when LA is much larger than LB, in the external region, the direction of E will be frozen and will not follow the change in the direction of B anymore. Okay? So, what are the predictions, what are the results as far as the emission from isolated neutron stars are concerned, talking about the polarization properties of radiation? I will just review a few examples starting from magnetars, which are sources with a ultra strong magnetic field, 10 to the 14 or more. And let me just remind that the magnetar persistent emission is thought to come from the reprocessing of thermal emission emitted at the surface by resonant Compton scattering onto charges that flow in the magnetosphere along the closed field lines of a twisted magnetic field. Just a movie to show how a twisted magnetic field is. So it will start again. It starts from a dipole, and then it is not a time sequence. It just illustrates how the field changes if I increase the twist angle. Okay. Of course, this twisted field is a non-potential magnetic field, which implies that currents must be there, and these currents will flow along the closed field lines. The currents are, we think, made essentially of electron-positron pairs, but okay, that's a different story. Of course, I mean, we can guess what is the initial polarization of radiation selecting a models for the surface emission of the magnetar, although this is still far from being a settled issue. But there is also another point here that the scattering, the resonance scattering by the electrons circulating in the magnetosphere will change the polarization state of the photon. I just put it as an example the ratio, or better the relationship between the different scattering cross-section for OO mode and OX mode. And one actually can show that the polarization degree and the polarization angle depend on the twist angle, on the charge speed, and on the geometrical angles. This was a model discussed by Fernandez and Davis and our group a few years ago. So if I proceed, I can show you how the polarization angle and the linear polarization fraction changes in this model by changing the twist angle. And you see that while the spectrum changes, also the polarization angle and the polarization degree changes in an even more dramatic way by changing the twist angle. Okay, just a few words because Roberto Taverna, who is talking just after me, will concentrate on this about the polarization of radiation coming from bursts and flares, which are emitted from magnetar sources. Magnetar sources emit different types of bursts, from normal bursts to the hyper-energetic giant flares. The current state of the modeling is that the magnetar bursts and flares likely originate in a hot magnetically confined pair fireball, according to the original suggestion by Thomson and Duncan more than 20 years ago. So what we have done, Roberto will discuss this in detail, is to solve the radiative transfer for the two modes in the surface layers of the fireball. And the quite obvious prediction that one can extract is that because of the scattering depth for the O mode is much larger than that for the E mode, one expects that the intrinsic radiation from the fireball is highly polarized, although the spectrum is indeed BB, black body plus black body like. So here is a plot showing as a function of the two geometrical angles, the polarization fraction and the polarization angle for a typical intermediate flare like those emitted by 1900 during the burst forest. And you see that the polarization fraction, at least for a given combination of the two angles, is very large indeed. Okay, thermally emitting isolated neutron star will typically the X-ray dim isolated neutron stars. These are 7 close by sources with soft thermal spectrum with temperature of few tens of electron volts and periods in the range 3-12 seconds. Emission is thought to come from the entire star surface, which has an inhomogeneous surface distribution, which is dictated by the magnetic field for a for the dipole. This goes like, T goes like the square root of cosine theta, where theta is the magnetic colatitude. We are not sure what is the radiation mechanism which is actually producing the radiation we observed in the X-ray range. As I said, it could be an atmosphere, it could be a condensed surface, perhaps with a very thin hydrogen atmosphere on top. Just to show you what comes out, I just report here the results for the phase average polarization fraction, according to calculation recently presented by Denis Gonzalez, Kanulev, and our group. This is the polarization fraction observed at infinity in the case in which the neutron star has an hydrogen atmosphere, fully ionized, magnetized hydrogen atmosphere. Please ignore this line here. I will discuss this later. Well, the colors here are perhaps not the, they are not the right ones, but anyway, and you see that in this case, you can have a very large polarization at infinity, at least for certain angles, but in the case of a condensed surface, the polarization is, well, not zero, but definitely lower, okay? So, I mean, the choice of, with all the other, keeping fixed all the other ingredients, the choice of the emission model is crucial to the polarization observables. So, very well, excellent. So, what about the future? As I mentioned at the beginning of my talk, there are a number of proposed missions. I listed here the 3 which I know better. There are other under study yet. The first one is called XP, Imaging X-ray Polarimetry Explorer, and it has already been selected as a NASA's next mission. Launch is expected late 2020. Then there is SHIPE, or XP as you would like. This is the X-ray Imaging Polarimetry Explorer, not much fantasy in choosing the names for these missions, which is still competing for ESA M4. And if selected, the launch is expected, well, according to the original schedule, again late in 2020, but perhaps a bit later. And finally, there is a Chinese-led mission, which is called the XTP, Enhanced X-ray Timing and Polarimetry Mission, which is a strategic priority space science program of the Chinese Academy of Science, which is scheduled to fly within 2025. The 3 missions as use the same polarimeter, which is a gas pixel detector polarimeter, which has been developed by the group of Costa, Enrico Costa and Paolo Soffitta, Bellazzini et al. At INAF in Rome. The main difference between the 3 missions is in the size of the telescope, and of course XIPE should have the larger effective area and XPE the smaller. So this is a sketch on how the gas pixel detector works. Basically, it exploits the photoelectric effect and the fact that the photoelectric cross-section depends on the polarization state. Then you can reconstruct the photoelectron track, and from this reconstruction you can compute the polarization observables. So finally, what we will measure when the X-ray polarimeters hopefully will fly. Well, at least one will fly. Well, first let me say that phase result polarimetry can probe the resonant Compton scattering model for magnetars and pinpoint the source geometry and physical parameters, which is one thing, especially talking about the geometry, that spectroscopy alone cannot do. This is an example of a simulated observation with XIPE. The next figure will show the same for XPE. Of a bright magnetar persistent source, which is this one, the IXP1RXS J1708, and indeed you see that the fit, don't ignore please this, so these are the simulated data, the dashed line, the blue dashed line, ignore the red one, is the model from which data were generated, and the full blue line is the best fit. So indeed, if you make a simultaneous fit of the flux, of the linear polarization fraction and of the polarization angle as a function of the phase, these are integrated in the 2.8 or 2.6 maybe, 2.6 energy band, you can recover the model parameter and have a confirmation, if this will be the case, of the validity of the model, including the values of the angles, of the geometrical angles. Okay, they say this is the same for XP, the same duration too. You see that the error bars are slightly larger because, of course, the detector has a less effective area. Second very important point is that X-ray polarimetry can univocally detect vacuum polarization, which is very important because this effect is still to be experimentally observed, although there are attempts in the lab to measure delta n. Let me say that X-ray polarimetry will not measure the difference in the refractive index. We just tell us that the refractive index are different. Okay, so I come back with the same picture as before. Pardon me, but this is should be referred to XP, not XIPE. That's Roberto's fault, which forgot to change the label on the figure. But the point is that if you generate the mock data according to the model, which includes QED, so with vacuum birefringence, then you get a nice fit. Of course, if you try to fit the same data with the model in which the QED effects are artificially turned off, then of course you get this. Okay, it's a warning that the time is up. Okay, I think okay, just a few seconds more. So, I mean, this will discriminate between the two different scenarios, QED on and QED off. Of course, we believe, of course, that QED is there, but this will tell us that effectively it is like that. Okay, this is again about the burst, but I can skip this because Roberto will talk much more extensively about this. So, thermally emitting neutron stars, this again I will skip. Just let me remind that thermally emitting the X-DINGs are not within the energy range explored by the current polarimetric missions, so it will be impossible to observe them with the scheduled missions, but there are soft X-ray polarimetry and polarimeters under study, and of course also in the case of X-ray dim isolated neutron star, it would be possible to discriminate between the QED and the no QED scenarios according to the polarization fraction. And finally, just a few words about a very recent work we did about the optical emission for one of the 7, RxJ 1856. Quite surprisingly, this source has a large, or relatively large, polarization degree, which is larger than 16%, and it's completely anomalous with respect to the neighboring dim field stars. You see these control stars here. This is the source, this is Q, this is U. So we are pretty convinced that the determination of this polarization in the optical B band with VLT is robust. And if you take into account for the different models, and you also take into account that we know the pulsed fraction in the X-rays, which is very small, is 1.2%, you put everything together, the models without any QED accounted for works only marginally. But if you actually include the QED, then the models work quite well. So I'm not claiming that this is the first direct measure of the QED effect, but within the models we explored, I hope that George agrees with me, it is like that. So these models are compatible with the measure only if QED is there. Okay, I think I will stop here and leave just my conclusion up there. Thank you.
We have time for a few questions. George?
Yeah, first, does it work? Okay. First, sorry for this notice, one should never quote error with 3 digits.
Sorry, I didn't understand.
You quote the error of the polarization degree with 3 significant digits, which is not the right thing to do. But it's not important. But more generally, I would say that I don't think that any body of physicists has any doubt that the vacuum birefringence, vacuum polarization is there. So if you know how to include it correctly, it's even no point in investigating the case when there is no this QED effect. QED, it is well-established theory, and so on and so forth. So it is not quite scientific approach. But as I told you, nevertheless, of course, this measurement of polarization is very important by itself. And I would even say that we have no doubt that the magnetic polarization, vacuum polarization is there. But you can use this to sort of justify your models of the temperature distribution over the surface, which is in a sense much less certain than the presence of the QED effect.
No, I agree, and I think I stressed this in the talk, during the talk, on the fact that there is no doubt that vacuum birefringence is there. Still, it is actively searched experimentally in the lab by a few groups around Europe, mostly in France and in Italy, because there is no direct experimental evidence for it. And I think it is important because it should be quite important to test experimentally one of the prediction of QED, which we know holds. And this prediction is about the self-interaction of the electromagnetic field with itself. Because vacuum birefringence is precisely that. So the vacuum birefringence, in a sense, implies that the index of refraction is influenced by the electromagnetic field itself. So the speed at which light propagates depends on the electromagnetic field itself. So this is a different way of putting this. But I think that this is an important, it will make, of course, we have the theory, but it will show with beyond any doubt that in the strong QED limit, Maxwell equations are not all right. And of course, it's a bit like general relativity. When you go from Newtonian theory to GR, the equations are nonlinear. And the same is with the electromagnetic field.
General relativity, you have several ways, several options.
No, I was not making that point, George, of course. I was just saying that the equation describing correctly the electromagnetic field in the more general situation are not linear. Okay. As the more general equation describing the gravitational field. So Einstein equation tells us that the gravitational field interacts with itself. And in this case, QED tells us that photons interact with themselves. This was the only point I would like to make.
Okay. Let us now...
Sorry. Yeah.
Interesting discussion, but we need to move on now to the next talk. This will be given by Roberto Taverna on the spectrum and polarization of magnetar flare emission.